to a slightly different topic. This topic is about the properties of signals. Signals are what we will be applying to systems. So, we should be very clear about the properties that different signals are expected to have. This also will be an elementary discussion. There will be more and more properties that we can ascribe to signals, and we will learn them as we proceed through the course. At the present stage, there are some very basic properties that signals must have. Signals are functions, and what we expect of a function. Now, saying this by emphasizing more strongly on this property than we did at the time we introduced the meaning of a signal, is that a signal must be defined for all values of the argument, must always be defined for all values of the argument. The signal must necessarily be defined for every value of the argument. That means, if the argument is time, for every instant of time the signal must take on some value, and by saying that it should take on some value, we mean some value within the range set. In this case, the range set is the set of real numbers. Now, on the face of it, this might seem a quite unnecessary stipulation, because obviously every signal will take on some value if you specify it, or so it seems. Well, to make the point that this is not a trivial stipulation, let us take an example, a most straightforward example, such as let x t be equal to 1 by t. This signal takes on a value, in the sense that I said a signal should take on a value for all points of time not equal to 0. That is, x t can be said to be finite for all t that is non-zero. However, we know what happens when x t tends to 0. When x t tends to 0, its value will rise without limit, and for t equal to 0, x t we can loosely say is infinite. Now, if we say that x t is infinite, that is not good enough, because this so called infinite is not a real number. Let us put that down. Real or complex number for that matter. In short, we will have to admit that in this case x t is not defined for t equal to 0. That is serious. Serious enough for us not to allow x t to be called a signal. X t does not qualify to be called a signal in its present form. However, we can do some repairs. We can make an artificial stipulation, a different stipulation for the time instant t equal to 0, and say x t is given by 1 by t for t not equal to 0, and say it is equal to 0 or whatever value we like for t equal to 0. This way, x t has been forced to have some value for all values of time, including t equal to 0. It is not infinite anywhere. And this kind of a piecewise specification, that is, a specification which defines the value of x t by giving different expressions for different points of time or different regions of time is perfectly all right. We will do this all the time, we consider it to be perfectly legitimate. And there are more examples of signals which are not properly defined. For example, suppose we take x t equals tan t. Again we know that tan x or sorry tan t tends to infinity as t tends to pi by 2. So, not apart from pi by 2, it will also tend to either plus infinity or minus infinity at 3 pi by 2, 5 pi by 2 and so on and so forth. So, in general about a signal or a function such as this, we can say that x t is undefined for t equals 2n minus 1 pi by 2. Is that right? N equal to 0, it is pi by 2, 3 pi by 2 and so on, it is right. So, this is another example of a signal which is not another example of a function which cannot be called a signal. What we will therefore restrict ourselves to are signals which are, so to speak, finite valued. Which is to say that the signal has a finite value for every instant of time. Let us take examples of finite valued signals. First example, how about x t equal to t? No problem here. This signal is finite, because as long as t is finite, t will be finite or x t will be finite, which comes to the same thing. However, at first sight people can raise objections. They can say things like, wait a minute, as t tends to infinity, let us make a plot of this function. It goes like this, this is x t and this is the t axis. People can raise the objection that x t seems to be finite around the parts which we have drawn, but that is not necessarily true as t gets larger and larger. Now, as t gets larger and larger, what are we afraid of? As t gets larger and larger, x t will also get larger and larger. In fact, as we see, it is always equal to t. But along the time axis, t is finite at every point, and therefore, x t is also finite at every point for that corresponding value of t. In short, there is no point on the time axis at which x t is not finite. Thus, x t as specified here is a finite valued signal and therefore qualifies to be called a signal. Let us take other examples, more dangerous looking examples, such as x t equal to t squared. I do not have to argue again from first principles for this second example. So long as t is finite, so long as t is a finite number, t squared is also a finite number, no worry there. Fine. 3, even more dangerous if we like, what about x t equal to e to the power t. E to the power t rises even faster than t squared does. In fact, it rises faster than any power of t. Yet there is no problem, because as long as t is finite, e to the power t will also be finite. It might be extremely large, but we are not afraid of something being extremely large, we are only afraid of something being infinite. We do not want it to be infinite, but it can be extremely large, there is no problem there. So, these are all examples of finite valued signals, signals whose value is finite at all times. But finite valued signals, while better than signals or functions that we discussed earlier, such as x t equal to tan t or x t equal to 1 by t, these functions are defined everywhere, but still they have the problem that they rise, they can, as we said earlier, increase without limit, and that is what is happening with x t, that is what is x t equal to t, it is happening with x t equal to t squared, e to the power t, all these functions. But there are other signals which do not increase without a limit. For example, what about let me make this separate set of examples, signals which are finite valued, but which do not rise without a limit. There are some very familiar examples here, such as x t equal to sin t, x t equal to cosine t. All these are examples of signals which vary as t varies, but which stay within limits, so to speak. You can think of more examples. What about this was the second example, then a third example such as x t equal to e to the power minus mod t. The third function perhaps is not so familiar, but it can be easily plotted. E to the power minus mod t may be expanded and written as e to the power minus t for t greater than 0, e to the power t for t less than equal to 0. Such a function appears like this. The familiar exponential decay for positive time and a backward decay for negative time. At t equal to 0, it takes on a value equal to unity. This is a signal which stays within limits, so to speak, in the sense that it never gets below 0, it never gets higher than 1. So, we can say that for this x t, the third example, we can say that 0 is less than e to the power minus mod t less than equal to 1, and this is true for every instant of time. So, these are signals which do not rise without a limit, but what exactly are we trying to say when we speak of a signal rising or not rising without a limit? This thing has to be discussed in a more formal manner, and in order to do this, I will go to the next screen and speak about the notion of the bound of a function or a signal. What do we mean by a bound? Suppose we have a signal x t. X t takes on various values for different points of time. Can we find a number which I will call b such that mod x t, the absolute value of x t, is never greater than b? If such a b can be found, then we will say that b is a bound on x t. let me put this down. If mod x t, the absolute value of x t, is less than equal to b for all time minus infinity less than t less than infinity, then we will say that b is a bound on x t. Signals which we have been accusing of rising without a limit will not have any bound at all. Signals which on the other hand we have been quoting as examples of those which stay within limits do have a bound, and that is exactly the formal meaning of saying that a signal stays within limits. Let us take some of the previous examples and see what we mean. Let us take for example x t equal to t. The first example we prepared for signals which were finite but not bounded, x t equal to can you just stop this for a minute? Now, let us take the first example that we had earlier, namely x t equal to t. Can we find a bound for x t? The argument of course is that we cannot, and the best way to prove it is to try to find a bound for it. Suppose I say that a bound is 10,000. Suppose we say that b equals 10,000. Sorry. The first example was stop. The first example was x t equal to t. Now, what kind of a bound would be large enough to ensure that x t never exceeds it or mod x t never exceeds it? The point is that for a signal like this there is no bound, because even if I take a very large value of a bound just to be safe, such as if we let b equal to say 1000, are we safe? Clearly not, because as soon as t exceeds 1000, that same 1000, x t will also exceed 1000. So, 1000 is not a safe bound, but this is not the only place where trouble will happen. Even if x t goes below minus 1000, which will obviously happen for t less than 1000 minus 1000, the same trouble will happen, because even here mod x t is greater than 1000. So, these are places where the bound will be exceeded and therefore, it will cease to be a bound. So, b equal to 1000 is not suitable as a bound for an x t such as this. What about b equal to say 10,000? Are we safe now? Again clearly not, because as soon as t exceeds 10,000, x t will exceed, in fact as soon as mod t exceeds 10,000, mod x t, making the argument a little briefer than last time, will also exceed 10,000. So, you would be in trouble again. Fine. So, of course, I can go on using larger and larger bounds, but the point is already made that no number can serve as a bound for an x t such as this. This is equally true of some other x t such as x t equal to t squared. Here too the problem is the same. Whatever t you choose, whatever b you choose, there will always be a t beyond which x t will exceed the b. The absolute value of x t will exceed the b. Third example, recall the same, x t equals e to the power t. Now, e to the power t is a little interesting, because for t less than 0, x t is bounded. X t in fact equals mod x t, because x t is always greater than 0, and this is invariably less than 1. So, it is bounded, but for t greater than 0, whatever bound you set, x t will exceed that bound very soon. In short, it rises without limit. So, these are all unbounded signals, signals for which a bound cannot be found. The bound unbounded signals. It is a fact that in signal and system theory, we try to stay away from unbounded signals, perhaps not entirely, but as far as possible our interest will be in bounded signals, signals for which a bound can be found. We need examples for this as well, and let us do that. Let us pick up a few examples. First, a signal like sin t. What sort of a bound can we find for sin t? Consider say b equal to 4. Is b equal to 4 a bound for sin t? It is, because we know that sin t, or rather in this case we are concerned with the absolute value of x t equal to sin t. So, we know that mod sin t is always less than 1, less than equal to 1. So, b equal to 4 is a perfectly valid bound for this kind of an x t, but this is not the only bound. The bound of a function is not a unique number. If it exists, it will exist in plenty. If it does not exist, it will not exist at all. There is in fact no signal for which only one bound can be found. If there is one bound, there are many bounds. If there is no bound, then there are no bounds. So, for example, b equal to 3 or 10 or 45 or 100 or even 1. The last is also a bound, because the definition of a bound is just that the signal, the absolute value of the signal should not exceed that bound. So, even 1 is a bound, in fact, it is the lowest possible bound for x t equal to sin t. X t equal to sin t has an absolute value that never exceeds 1. So, 1 is also a bound. A bound need not be greater than 1 in this case, but all these others like 3, 10, 45, 100 etc. are also valid bounds for x t. Now, cos t is a similar signal, has the same kind of properties and in fact can have all the same bounds. Every bound given above for sin t is also a bound for cos t. What about, say, going a little off track, x t equal to 4 cos 3 t. What can we say is a bound for this signal? This signal has a frequency, radian frequency of 3, but that does not concern us because that does not affect the amplitude of the signal. What affects the amplitude of x t is this coefficient outside, namely 4, and because there is 4 outside, we know that a signal such as this can swing from -4 to 4. Thus, we need B to be greater than or equal to 4, but certainly B exists. So, this is also a bounded signal. Let us try to construct one more example. In fact, refer to the example we dealt with earlier. What about x t equal to e to the power minus mod t? E to the minus mod t we found confined itself to the range 0 to 1. In short, we know that 0 less than is less than e to the minus mod t, which is less than equal to 1. Hence, a bound for e to the power mod t would be anything that is greater than or equal to 1. Any of these would be a bound for e to the mod t, but there is a possibility of going wrong in understanding the meaning of a bound, and therefore, let me give you some examples where the bound must be understood more carefully. Consider a signal such as x t To continue with our discussion of bounded and unbounded signals, here are some signals which probably might appear to be bounded for the uninitiated, but which are actually unbounded. So, the first example is of x t equal to say 2 minus t squared. Let us plot this signal just roughly on the side. This is x t equal to 2 minus t squared. It achieves a maximum of 2. Is this a bounded signal? That is the question. Though it appears to be bounded from above in the sense that x t is less than equal to 2 for all t, x t is not a bounded signal simply because a bounded signal should be bounded both from above and below. That is why we say that mod x t should be bounded. It is not x t alone that must be bounded, but mod x t, and in this case you find that for in the range of negative values x t can go below, can go down and down without limit. In fact, it goes towards minus infinity as t tends to infinity or t tends to minus infinity. So, though x t is bounded, mod x t is not bounded here. And it is important to note that boundedness is a property of x t only when mod x t has a bound, not when x t has a bound. So, both in positive and in negative values x t should not change without limit, should not vary without limit. This is a sufficient example to point out that boundedness is to be understood a little more carefully. Now that we have a general idea of what we mean by a bounded signal, let us close the matter by saying that we expect signals to be bounded for most of our studies. For apart from mathematical considerations, there are also physical considerations. In real life, every signal we meet with, every signal we deal with is always bounded. The voltage that comes out of a source is always limited both in its positive and negative value by the kind of circuitry that has been used to generate that voltage. That is one example of a signal being bounded. Now, you can take any other kind of example. The sound that I make out of my throat has a bounded amplitude, because there is only a limited amount of power, only a finite amount of power that I can produce with my throat. So, speech signals, music signals, any of these signals that come out of musical instruments or loudspeakers or human voices, all these are bounded. The brightness of a picture that comes out of a television set is also bounded, because it cannot produce infinite power at any instant of time. So, fundamentally we may say that all physical signals are inherently bounded because any physical source of signals can produce only limited signal power. This can be our justification for confining our interest to bounded signals. So, to summarize, what do we know about signals? These are of course some of the properties that we have discussed so far. There are some more properties I will be going into right now in a moment. First is that some signals or some functions are not even finite at certain points. Example, tan t 1 by t, these are examples. The next category is of signals which are finite but not bounded. Examples, x t equal to t, x t equal to 1 minus t squared, x t equal to e to the power t. These are examples. The third category, the ones which we like most, are bounded signals. Bounded signals have examples like cosine t, then e to the power minus mod t, then x t equal to a constant such as say 4, that is also a constant signal, therefore bounded. All these are bounded signals. Now, we should note that signals of the first category mentioned here are not recognized as signals at all. We will not in fact deal with them as far as possible. The second category we will also avoid, but sometimes we will have to face such signals and deal with such signals. The third category is almost essentially what we will deal with, and we already know why, because physically also only signals of the third category can be generated by sources. There is no physical phenomenon which can increase or decrease the value of a parameter, namely the signal of our interest, towards infinity or minus infinity without limit. Everything in the real world is limited by the process which generates it. So, that closes that discussion. Next thing we will talk about some examples of signals. Sorry, just cut that. There can be other properties of signals, and we will just discuss one more at the present time. It is better to wait for them when these properties emerge naturally for us. Right now, we will speak of another property called, which can be called a symmetry property. The sort of symmetry that a signal can have may be of many kinds. Periodicity is one kind of symmetry. What do we mean by saying that a signal is periodic? When we say that a signal is periodic, we mean that it repeats itself over and over again an infinite number of times after a certain length of time. Mathematically, we will say that x t is periodic if it is equal to a time shifted version of itself, x t equal to x t minus t. What we mean by that is this: if we have x t over here, let us say I plot x t like this, then I can designate this point to be t and this next point to be say 2 t. Likewise, somewhere behind over here we will have minus t. Now, these numbers t, minus t, 2 t are significant with reference to this signal, because if I slide this graph that I have drawn of x t towards the right by t units of time, then what would essentially happen is we get a new graph. I will call this new signal say x prime t equals x of t minus t. This point would come over and land up here. This point would come over and land up here. This point would come over and land up here. But even if we shifted the time axis in this manner, as I have shown, the function would shift along with the time axis, but yet it would end up looking exactly the same as before because of its symmetry, because of its periodic nature. This cycle which I have drawn over here would turn up over here. So, this point has come over here. Now, this second cycle would turn up over here. This so that, for example, this point would land up over here. The third cycle would move further to the right and come here. So, that a point such as say this one would come over here. So, everything has moved to the right, but because this shifted signal is indistinguishable from the earlier signal, we will say that this signal, the new signal and the earlier signal are identical, and we will denote that by writing what we have written over here, that x t equals x of t minus t. So, periodicity is a kind of symmetry. In spite of making a change in the signal remains the same, and that is the essential definition of symmetry. In fact, when we subject a signal to a change and after undergoing the change it still ends up looking exactly as before, we will say that the signal has a certain symmetry. This is a periodicity, and periodicity is one kind of symmetry. We will just discuss one more kind of symmetry, and that is called even symmetry. This is the second kind of symmetry we are speaking of. Even symmetry is the property because of which if we invert a signal about the vertical axis, it still will look exactly the same. If we reflect a signal is what I mean. So, suppose we take a signal like this. Let us say the signal is like this, and it is 0 for all points greater than 2, and let us say this is minus 3 by 2, this is 3 by 2, something like this. Now, consider this signal, let us call this x t, and try to understand what happens when you plot x of minus t. X of minus t would look exactly the same as x t. And because it looks the same, in spite of being subjected to a reflection about the vertical axis, we will say that this signal is even symmetric. X t is even symmetric. There is another property that is often spoken of side by side with even symmetry, and that is called odd symmetry. It is not really a symmetry, but people tend to call it that. So, I will just note it here. Note that even symmetry is the property by which x t equals x of minus t. Odd symmetry, on the other hand, is the property by which x t equals minus of x of minus t. Let us take a signal. that is an example of odd symmetry. This is an odd symmetric signal, because I can show it in two steps. The first step, I will reflect it about the time axis. If I do that, I will get x of minus t. This is x of minus t and this is t, and in the third step I will invert it or reflect it about the horizontal axis, the time axis, to get minus x of minus t, minus x of minus t. It would again look like this. This is odd symmetry. We will say that x t is odd symmetric if minus x minus t is the same as x t. We will say it is even symmetric if x t is the same as x of minus t. So, even and odd symmetry are two nice properties that a signal might or might not have. But interestingly, if you take any arbitrary signal, it can always be broken up into a sum of two parts, one which is odd symmetric and one which is even symmetric. So, just as a diversion, an interesting diversion, let us consider what happens to the decomposition of a signal, how we actually decompose a signal into even and odd parts. Our objective is to take an arbitrary signal x t and express it as a sum x e of t, that is the even part, and x o of t, that is the odd part. Since x e of t is an even part, x e of t will be equal to x e of minus t and x o of t will be equal to minus x o of minus t. The interesting thing is that this can be done for any signal, by which of course we refer to any finite valued signal. It need not even be bounded in order for us to do this. Let us take examples. Let us take for example x t equal to t. X t equal to t looks like this, as we already know. It is not a bounded signal. Is this an even signal or an odd signal, or if it is neither, can we decompose it? In this case of course, it is trivial. This signal is already an odd signal. So, how do we decompose it into an even and odd part? Very simple. We will say that x e of t, the even part is 0, and x o of t, the odd part, equals t. So, x t is equal to x e of t plus x o of t. Sounds like cheating, but that is happening only because the signal is too simple. Now, let us take another signal. Let us take a signal that looks like this. I will draw the graph instead of describing the signal mathematically. Let us consider a signal that is 0 for all negative time, and for positive time it is like this. I think it is evident to you by now that this is neither an even symmetric signal nor an odd symmetric signal, but it can be decomposed into an even and odd part. Let us just put down some values here. Let us say this is t equal to 1 and let us say its value at this t equal to 1 is also unity. So, let us say this is the signal. How do we find its even part? All we do is take x t and add it to x of minus t and divide the sum by 2. So, x e of t can be shown to be x t plus x of minus t divided by 2. Likewise, x o of t equals x t minus x of minus t by 2. So, if we take x t over here as we have shown and try to construct x e of t out of this, it is a straight line with a slope of unity between 0 and 1, and after that it is a constant, that is a line of 0 slope and a value equal to 1, and for t less than 0 it is equal to 0. So, going through the calculations you will find that x e of t can be plotted like this. This is the even part. The odd part would be this. This is the odd part of x t. Now, see what happens when you add these two. You will find that for t greater than 0, x e of t in this instance is exactly equal to x o of t. So, that for t greater than 0, x t simply equals 2 x e of t or 2 x o of t. On the other hand, for t less than 0, x t x e of t is the exact opposite of x o of t, is exact negative of x o of t. So, x e of t equals minus x o of t. So, that x t equals 0. This true for t less than equal to 0, and we have covered x t at all points. So, this is a simple decomposition. The formulas to be used are these. They tell you how to decompose a signal into an even and an odd part, and finally, to compose a signal from its parts is to simply add the two parts and you get x t. So, this is an interesting exercise in using certain symmetries of a signal to decompose the signal. In fact, there is always going to remain an intimate relationship between the symmetry properties of a signal and its decomposition in various ways. So, symmetries are intimately related to signal representation. Signal representations. How the relationship is exactly formed is a little deep for us to cover in this course, but it is still a worthwhile point to remember. We just used even odd symmetry and showed that a signal could be represented as a sum of even and odd parts, and that it could be decomposed into these parts, and that it could be done for any signal at all,